in this axial loading problem, we're going to have temperature change involved with the problem. So here's what it looks like. We've got a stepped bar. Everything's in millimeters in this case. And at the step, we've got a 5 kilonewton applied load. But we also are seeing a temperature change. The gap at the end, which is 1/4 of a millimeter, is there when the temperature is 15 degrees C and before the load is applied. So we want to know what happens when we raise the temperature to 30 degrees C, so a change in temperature of 15 degrees, and apply the load. We want to know what's going on there. We have the properties of aluminum as 70 gigapascals for the Young's modulus, and we also have the coefficient of thermal expansion given as 24 times 10 to the minus 6, 1/degrees C. Now, when we look at this problem, there's really two possibilities here. The first one is that when we apply the load and the temperature change, that the deflection is less than the gap. So it doesn't fill the gap, and so what we have then is a statically determinate problem. Very easy to solve. The second possibility will be that the deflection is such that the gap is completely closed. And so in that case, our free body diagram shows that we have reaction forces on both ends. And since we only have one equation of equilibrium, the sum of the forces in the x is equal to 0, we have a statically indeterminate problem. So, how do we solve this? Well, first of all, we have to make an assumption. Which of those problems do we have? Is the gap going to be closed or is it not? So, if we do it the first way, we assume that the gap doesn't close. We go ahead and work the problem. Well, how do we know if our assumption was correct or not? What we do is look at the total amount of deflection and make sure that it's less than the gap, because if we, for example, were to calculate based on the fact that it's not going to close the gap and the deflection comes out to be 1/2 millimeter, then we know that that's not possible because the gap is only 1/4 of a millimeter. The other possibility is just to make the assumption up front that the gap does close. So how do we know if our assumption is correct? Well, at the end, we'll look at the force on the right end. If the gap does close, then there will be a compressive force there. And so if the force is as we've drawn it here in the direction of that, in other words, it comes out to be a positive number, then we know that that our assumption was correct. If it ends up being the other direction, it would say that that end part of the rod was under tension, and that's not possible because the wall can only exert that compressive force on the rod. So we're going to take the second approach here. We're going to assume that the gap is going to be closed. Now, one thing about using SI units is that, again, I see a lot of students will make a mistake working here because you've got a lot of things going on, millimeters, kilonewtons, gigapascals, etc. So I recommend that you express all your quantities in these basic units of newtons, meters, and degrees C. So for example, the Young's modulus is given as 70 gigapascals. Remember that a pascal is a newton per meter squared, and a giga is e to the 9. We convert our lengths into meters, our force into newtons, the diameters into meters, and also the gap, the 1/4 of a millimeter, express that in meters as well. So here's our free body diagram of the entire structure, and again, it's statically indeterminate because we have one equilibrium equation, which is the sum of the forces in the x. By doing that, we can express the force on the right in terms of the force in the left, but one equation, two unknowns, so we can't solve the problem here. We'll go ahead and calculate the cross-sectional areas here for the two segments here, and again, the units are all meters, so our areas come out in meters squared. Alright, so now we're ready to for a statically indeterminate problem. In addition to equilibrium, we need compatibility. In other words, we need to involve the displacements. And since we're assuming that the gap is going to be closed, what we're saying is that the total change in length of the bar is going to be equal to the gap. And our equation for axial growth, PL over AE, and of course if temperature change is included, then we have alpha times the change in temperature times the length as the second term of that. So if we look at the two segments, we've got this starting to get lengthy equations, but again all it is the deflection of the left segment plus the deflection of the right segment is equal to the gap. So we still have to calculate. Let me go back for just a moment. We see that we have the internal forces PAB and PBC. So we need to write those in terms of the reaction forces and the applied load. If we cut through between A and B and do a free body diagram there, we see that the axial force in that segment is equal to the reaction force. And if we make a cut through BC and look at everything to the left of the cut, then we can calculate that the force in segment BC is equal to the reaction force on the left minus the applied force F. Okay, so let's go back to that equation that we have, and now let's rearrange that a little bit, or actually first thing we're going to do is take the axial forces, the internal forces, and we just wrote those in terms of the reaction force to the left and the applied force F. So we'll just make that simple substitution and then rearrange our terms somewhat so that we isolate what we're trying to solve for, which is R of A, on the left side. So everything on the right side is known, and so RA is the only unknown in this entire equation. So we'll put the numbers in for that. And again, the nice thing about switching to consistent units is when you get to a long equation like that, as long as everything's in consistent units, we know, for example, when we solve for R sub A, it's going to come out in newtons, and so we don't have to write the units for every step right through here. But you can see we've just substituted in all of the knowns here. The temperature change is 15 degrees C, and we're able then to solve for R sub A. So in a couple of steps here, notice that we've isolated R sub A on the left side, and do the math here, it comes out to be 3,381 newtons. That's the reaction on the left side. Okay, we saw earlier from our free body diagram that the reaction on the right side was equal to F minus R of A, which in this case turns out to be 1,619 newtons. So the 5,000 Newton load is shared as shown here. Now, we said earlier that if R sub C comes out to be positive the way that we've drawn it, then we know that there's a compressive force between the end of the rod and the wall. So our assumption was correct that the gap is closed and that right hand part of the rod is under compression. Now, to be able to calculate the stresses, of course, we have to go back to the internal forces. Remember that the force in the left segment AB is simply equal to the reaction force at the left, or 3,381 newtons. We also saw again that in the segment BC that our axial force, our internal force, was R of A minus F, so it's minus 1,619 F. So again, tension on the left side, compression on the right side. Calculate the stresses, we simply divide by the cross-sectional area. And again, we're using consistent units all the way through, so our stress comes out to be in newtons per meter squared, which again is a Pascal. And now when we get ready to do our final answer, then we use the appropriate prefix for our SI units, and so that works out to be 3.51 megapascals. In segment BC, again, we're in negative value for P, and so a negative value for stress. So that one's in compression, 5.15 megapascals. And so our solution we report our stresses as shown. Now, there is a variation of this problem we can look at. We saw that when the temperature change was 15 degrees, in other words, when the temperature was 30 degrees, 15 degrees above the starting temperature of 15 degrees C, that the gap was closed and we had developed compression in the right-hand part of the bar here. So we could ask, what temperature will cause the gap to close exactly? Well, before the gap closes, as we noticed, we have a statically determinate problem. And in fact, there's no loading on the right-hand side of this, in other words, segment BC. So when we do a free body diagram here of AB, we find, of course, that that we're under a tensile force of 5,000 pounds in segment AB. And we do the free body diagram of BC, then of course we find out if we look at everything to the right of the cut, there is no applied load, and so the internal force there is equal to 0. Makes sense. That part of it's just going along for the ride until the gap closes. So if we look at the total change in length, we have PL over AE plus alpha delta TL. We have that for segment AB, but since the loading on segment BC is 0, we can leave one term of that off. But of course, BC still will change length due to the temperature change, so we do retain that term. And we know all of this except for delta T in this case, because we're going to take this temperature change, this length change, and set it exactly to the equal to the gap, and that will yield the temperature change that causes the axial growth to be exactly the same as the gap. And so when we solve for that, solve for delta T, it comes out to be 13.1 degrees C. And so since the problem asks what temperature does the gap close, we have to add the 15 degree starting temperature plus the 13.1 that we just found for a delta T. And so at a temperature of 28.1 degrees C, that's when the gap closes. So anything temperature above that, we will start to develop compressive stresses on the right side of the bar. Anything less than 28 degrees, we don't. And so if we make a plot of this solution, again, we started here at 15 degrees C, and that was the temperature for which we had the quarter of a millimeter gap. And as we increase the temperature all the way up here to 28 degrees, you can see that in segment AB we simply have that constant tension due to the 5,000 Newton force, and there is no stress on segment BC. As soon as we go above 28 degrees, though, you can see that we start to develop higher compressive stresses in both of the segments. Now, segment AB, again, because of the force that's applied, does begin in tension, but as the temperature goes up, the compressive force due to the change in length that's constrained becomes larger than the tensile force that was there to begin with, and so that segment goes into compression as well. And you can see when we get up to 50 degrees C, so these aren't really huge temperature changes, we start to develop some pretty large stresses. And so when we have temperature change as a design consideration, a lot of times we will leave a gap to allow the bar, the axial member, to expand without generating these stresses. If we have a lot of temperature change, it is possible, of course, to either fail the material by getting the stress too high, or because these are compressive stresses, it's also possible that we could cause the bar to buckle, which we'll talk about in a later lesson.